that is probability of error given 0%. Okay, so let's remember Z is equal to 0. Sigma squared is equal to NB N0 over 2TS. And let's figure out the average probability of error. The probability of error is equal to the probability of error 0, probability of 0, plus the probability of error is 1, probability of 1, which is equal to, okay, let's substitute in the 0 here. We get 1/2 RF C NB over 2 sigma squared, and over here we get 1/2 RF C NB over 2 sigma squared, so that's the same. Probability of error given 0% is the same as the probability of error given 1%. So we end up with 1/2 RF C of NB divided by root 2 sigma squared, but I can substitute that in with NB N0 over 2TS. Times, if I take, because these are equal, I can take them out, and I end up with probability 0 plus probability of 1. What's the probability of 0 plus the probability of 1? 1. Must be 1, because it doesn't matter how I divvy these up. Taken together, the probability of them is 1. So I end up with 1/2 RF C. I can make some simplifications here. That 2 cancels with that 2. And I end up with root, this square root of NB in the denominator takes out a square root of NB in the numerator. I end up with NBTS over N0. So there's your probability of error for the example system that I gave. In defining that system, I did everything optimally. I didn't explain why I did the things that I did, but I ended up with the best possible probability of error. It turns out this is the best possible probability of error as long as 0 and 1 are equally probable. If they're not equally probable, then this is no longer optimal. I just want to point out a couple things here. Firstly, RF C looks like this. It's a monotonically decreasing function. So as its argument gets bigger, it gets smaller and smaller. So in order to make probability of error go down, what I need to do is I need to make this as big as possible. One obvious way to do that is to make N0 as small as possible. So in other words, the intuition there is if there's less noise, so N0 is like the noise intensity. If there's less noise, then this becomes bigger, and therefore the probability of error goes down, so that's obvious. There's something a little misleading here in the numerator. So it looks like NB times TS. For one thing, it looks like if I take more samples, then if I take more samples, then it seems like the probability of error should go down. But in fact, there is an interaction fact, there's an interaction between NB and TS. If NB goes up, TS has to go down. So what I'm assuming is that the bit time is constant. So if for example, I have 5, NB equals 5, then TS has to be 1/5 of NB. On the other hand, if NB equals 10, then TS has to be equal to 1/10 of NB. So in fact, NB times TS, what does that equal to? What the sampling time is equal to the total. If you can think of it this way, the sampling time is well, let me back up. NB is the number of samples per bit. TB is the total duration of time that I can spend on one bit. TB governs the data rate, so therefore TB is a parameter that you want to fix more than NB or TS necessarily. So the time between samples can be thought of as the time for an entire bit divided by the number of samples per bit. So if I substitute that back in out here, in fact, there's no dependence at all on the number of samples or the sampling time. What I get is 1/2 ERF C root TB over N0. So in other words, it doesn't matter how fast you sample. All that matters is the time that you spend on a bit. Because the bit rate, if you think about it this way, if the time per bit is 1 second, then you have 1 bit per second. If the time per bit is 1/100th of a second, then you have 100 bits per second. So in order to get a smaller probability of error, what you need longer bit time. So in other words, increasing the bit rate works against you as far as error probability is concerned. I have a few other remarks about this, but I think I'm running out of time, so we'll leave them for the next time. Any questions? So like I said last time, I'm writing up my notes. Hopefully they will be of some use to you. I'll start posting them starting probably this afternoon. So the way it's going to work is it's sort of like a book, except I'm filling in the chapters as I go. So you'll see how that works. Any questions? Yeah.
Where was the amplitude of the signal fit into?
The amplitude of the signal. So remember we had the amplitude fits in here. Basically, that expresses the amplitude of the signal. So basically, what that would do is it would scale the mean coming out of the filter. So that would show up on these NB terms.
If you're just raising the amplitude, then you're drowning out all your error.
I did right.
That's
Speech
right.
and a half
So
is
basically,
that.
if you crank up the volume, then
Nice.
you get.
Geometry or
Any other questions?
yes.
Okay, we'll see you on Tuesday.
In the class.